Okay, guys, welcome. Today we're going to talk about the idea of growth, and we're going to compare linear growth versus exponential growth. Now, linear growth is what we've really done so far, and that occurs when a quantity grows by the same absolute amount in each unit of time. Now, when you have linear growth, you have something like y equals mx plus b, where b you can think of as some sort of starting point, and most of the time we refer to that as the y-intercept. So of course, this is like your starting point. And this m is sort of your growth for each time period. And of course, most of the time we refer to that as the slope. Now, exponential growth occurs when a quantity grows by the same relative amount, so by the same percentage in each unit of time. So when you have exponential growth, you have something like this. So you have something like a times b to the x power, and a lot of times we'll even write this as a times 1 plus p to the x, where p is the percentage change. And here a would be some sort of a starting point. All right, so that's sort of the difference between linear growth and exponential growth. Now, in each of these following situations, we're going to state whether the growth or decay is linear or exponential, and then we'll answer the associated questions. Now, in part A, we have that the number of students at Wilson High School has increased by 50 in each of the past 4 years. If the student population was 750 4 years ago, what is it today? So since we have that we're increasing by the same absolute unit or the same absolute amount each time, this would be an example of linear growth. So we know that we're going to have something like, for part A, y equals mx plus b. Now we know that in this example, we're starting at 750 4 years ago, and we're increasing by 50 each year. So our m, or our slope, is going to get replaced by 50, and our b is going to get replaced with 750. And of course here, x represents the number of years past when it was 750. So for the number of years past when it was 750, to answer this question, we want to make x equal to 4. So it'd take 50 times 4 and add that to 750. And 50 times 4 would give me 200. And when we add that to 750, we would get 950. Okay, so that's part A. For part B, we have that the price of milk has been rising 3% per year. Now, if the price of a gallon of milk was $4 a year ago, what is it now? Now, since you're increasing by the same percentage, this is exponential growth. Or in this case, since it's, it's rising, so exponential growth. So again, we want to think of it as either y equals a times b to the x. And in this case, since we have the percentage, it's going to be easier to think of it as 1 plus p to the x. So now in this case, we're rising by 3% per year, and we're starting at 4. So we're going to have y is equal to 4 times 1 plus 0.03 to the x power. And of course here, x is the number of years past when it was $4. Right, so here I want to make x equal to 1, and I'm going to get that y is equal to 4 times 1.03 to the 1 power. Right, so it just becomes 4 times 1.03, and this will give us $4 Right, so that's part B. Now in part C, we have that tax law allows you to depreciate the value of your equipment by $200 per year. If you purchased the equipment 3 years ago for $1,000, what is its depreciated value today? Well, again, we're decreasing by the same amount each time, so this is linear. And since the amount's getting smaller, we usually refer to that as decay. So here we're going to get something like y is equal to, now we're losing 200, so this is minus 200x plus 1,000. And of course, since we want x to be the number of years past when it was 1,000, we want x to be equal to 3 here. So we're going to get y is equal to negative 200 times 3 plus 1,000. So we get negative 600 plus 1,000, which will give us 400. So now it will be worth 400. Okay, part D, we have that the memory capacity of the state-of-the-art computer storage devices is doubling approximately every 2 years. Now, a company's top-of-the-line drive holds 16 terabytes today. What will it hold in 2 years? Now, there's a couple different ways that we can think about this. If we think of it as y equals a times b to the x, then we're doubling each time. So we're going to make b equal to 2 here, right? And of course, the other way to think of it, if you were to think of it as a times 1 plus p to the x, doubling is a 100% increase. So you would make p equal to 1, which would also lead you to 2 for your b term there. Okay, now we're starting at 16 terabytes, or multiplying that by 2 to the x. Now here we have to be careful because it's doubling every 2 years, right? So we're not doubling every year, it's every 2 years. So when we want to know what will hold in 6 years, I need to either make x 6 over 2, which would make it 3, right? So we get y is equal to 16 times 2 to the 3, because we're going to get 3 doublings that occur within 6 years because it's every 2 years. So we're going to get that this is 16 times 2 to the third, which is 8. So for 16 times 8, we're going to get I believe that's going to be, so we'll get an 80 plus a 48, so we're going to get a 128. Okay, and then for part E, we have that the price of high definition TV sets has been falling by about 25% each year. And if the price is $1,000 today, what can you expect it to be in 2 years? So now this time, again, we're decreasing by the same percentage each year. Okay, so now we're going to have that this is y is equal to a times 1 minus p now to the x power. So of course here, we're going to have y is equal to, now we're starting at $1,000 today. So that's my a value. And if we're decreasing by 25% per year, this is minus 0.25 to the x power. So I'm going to have 1,000 times 0.75 to the x power for my equation. Now we want to know what's this going to be in 2 years. So I need to find out, well, what's y when x is 2? Okay, so if we enter this into the calculator, I need to do 0.75 squared. And then I need to multiply that by 1,000. And that's going to give me that y is equal to 562.50. All right, so we get that in 2 years, we can expect it to be worth about $562.50. Now, there's several other examples that you can look at if you feel that you need more examples, and they focus on the concept of doubling time. You can look at the parables on pages 475 through 478, although we're going to dedicate an entire video to doubling time. Okay, now some key facts about exponential growth are the following. Now, exponential growth will lead to repeated doublings, right? Now, with each doubling, the amount of increase is approximately equal to the sum of all preceding doublings, right? So you're going to get repeated doublings with a certain amount of time that passes. Now, exponential growth, of course, can't continue indefinitely, right? After a short amount of doublings, exponential growing quantities are going to reach impossible proportions, right? So for example, you can think of the world population as growing exponentially, but the problem is that after a while, you're going to run out of room and you're going to run out of resources for that doubling to continue. So in most cases, exponential growth cannot continue indefinitely. Now, one last example, we're going to say that a town's population increases in 1 year from 100,000 to 110,000. Now, if the population is growing linearly, then at the end of the second year, what will it be? If the population is growing exponentially, then at the end of the second year, what will it be? Okay, so first we have to do this for linear growth. Now, in linear growth, how much are you growing by each year? Well, let's take a look. So it's the same absolute amount. So if I subtract 110,000 by 100,000, I'm going to get 10,000, right? So lost my headset there, but we're good. Okay, so then we get 10,000. Okay, so that's how much we're increasing in, well, in this case, yes, just increasing by. So this is going to be my M term. Stop. Okay, 1 second here. So our 10,000 is like our M here. Now our starting point is 100,000. So we're going to have something like Y is equal to 100,000 plus 10,000x. All right, just sort of switch the order here, but the same idea. So now I'm going to make x equal to 2 because I want to know what's it going to be at the end of the second year. So this is going to give me y is equal to 10,000 times 2 plus 100,000. So I'm going to get y is equal to 120,000. Okay, and then for part B, we want to know that if the population is growing exponentially, then at the end of the second year, what will it be? Well, now we need to find what's the percentage change. So we need to do new minus old over old. So we're going to have 110,000 minus 100,000 over 100,000, right? New minus old over old. So that's going to give us 10,000 over 100,000, which is going to come out to be a 0.10 or a 10%. So now again, remembering that our model is y is equal to a times 1 plus p to the x, we're going to have that our equation is going to be y is equal to 100,000 times 1 plus 0.10 to the x power. Now, of course, we want to know what is it at the end of the second year, so we're going to get y is equal to 100,000 times 1.10 squared. So once we do that, we're going to get that this is, just enter this into the calculator, so we got to find out what 1.1 squared is. And then multiply that by 100,000. And we're going to get that y is equal to 121,000. So at the end of the second year, when we're growing exponentially, we're going to have 121,000. All right, so that concludes this video on comparing the growth between linear models and exponential models. I hope you enjoyed, and I'll see you next time.